Hello everyone. We are group 18, Penguin Shogun. Shogun means, Shogun is the Japanese, that means army general in English. And I am Hu Ruitong. And I'm going to talk about my midterm presentation. First, we choose the type of the clock we choose for our midterm presentation is pendulum clock. And the reason why we choose this topic is because in nowadays we have invented quartz clock, atomic clock, and many different types of clocks to measure time precisely. But however, we're more curious about the primitive ways ancient people used to measure time centuries ago. So since pendulum clock is one of the earliest tools that human beings used for measuring time, we choose it as the topic we're discussing. And what is a pendulum? A pendulum is a rod hanging vertically from its top end, right here, or a weight called a bob hanging from a string. And the bob is the gray ball in the picture here. And a pendulum swings from side to side due to the force of gravity. And about the studies of pendulum, in 1602, when the famous Italian scientist Galileo Galilei was at the Cathedral of Pisa, there blew a gentle breeze, and he noticed that the chandelier on the domed ceiling was waving back and forth at the same speed, and therefore he started to dig into the phenomenon of pendulum. And as he discovered, the clever thing about a pendulum is that it always takes the same amount of time to make one complete swing. And the first pendulum clock that human invented is in 1656, that Dutch scientist Christian Huygens built. And what's special about this pendulum clock is that its timekeeping accuracy shrinks from 15 minutes to 15 seconds per day. And here's the end of my presentation. Thank you.
Hello everyone, I am Chou Si Hao, aka Tony Chu, and my student number is 109610005. And I'm going to introduce the pendulum model. First, I have to introduce the arc length, and I use symbol S to be arc length. And S will be the rod length L multiplied by theta. And by Newton's second law, we can derive the equations of motions. Mass multiply acceleration. And acceleration will equal to the second derivative of arc length. And we can derive the equation left on the left-hand side. And it equals the tangent force, which means the gravity force. And its tangent components will be mg multiplied sine theta. And we should plus it should be negative because it is a restoring force. And we can derive the equations of motions. And we can get the following results. And if we use the small angle approximation, that means when theta is small enough, then sine theta will approximate theta. And the equation will becomes the second derivative of theta plus g over L multiply theta equals 0. And we can get the solution to be the combination of sine function and cosine function. And inside the cosine and sine, it will be omega t. Omega is the angular frequency, and the angular frequency equals to the square root of g over L. And then we can derive the period t, which is 2 pi over omega, and it will become 2 pi multiply square root of L over G. It's choose that again, and we are going to take a look at animation of the solution, right? The pendulum model, yeah. And Albert 1 create the animation of the solution, and we only made cosine function, and it is totally same as not totally, I mean approximately like sine wave. Yeah, the animation will look like. So we only choose the cosine function. And next, we're going to, this is the code. Yeah, skip it. And next we have to discuss if we consider the air resistance and the pendulum, in reality, the amplitude will decreases with time. So we assume that the formula solution need to multiply by exponential minus ct, and c being the constant, and it will be like the damped oscillations. This is one kind of damped oscillations, and we think the pendulum will damp oscillate like this. So we choose this one. Yeah, and this is the code of the damped oscillation. Okay, and afterwards, let's think about what if the pendulum clock was shaken, and the amplitude will be disturbed, and the clock lost accuracy. So maybe we should create a new clock to escape from the gravity. And the spring came to our rescue in 1950s. Though there is some dispute as to whether the balance spring was invented by Hooke or Huygens, and with the likelihood being that Hooke first had the idea about the springs, the F equals kx, yeah. But Huygens built the first functioning watch that used a balance spring. Thank you.
Hello everyone, my name is Wang Youjing, and my student number is 1096100008, and Wang Youjing. I'm going to start my midterm project representations, and I'm going to introduce another mechanical way to calculate time spring and balance spring. Balance spring, which usually can be found in watch, is a spring attached to the balance wheel in mechanical timepieces, and its Chinese is 游丝. In 1675, Huygens carried forward the balance spring. He invented spiral balance spring with round-shaped wheel, which made the accuracy of clock improve greatly. The balance spring is an essential adjunct to the balance wheel, causing it to oscillate back and forth. We can find balance spring in watch frequently. Isochronism. A balance spring will obey Hooke's law. The restoring torque is proportional to the angular displacement. That is what Hooke's law tells. When this property is exactly satisfied, the balance spring is said to be isochronous, and the period of oscillation is independent of the amplitude of oscillation. The modulus of elasticity of materials is dependent on temperature. Early on, steel was used. However, these springs would gradually weaken and the watch would start losing time. And the solution is in 1833. E.J. Dent experimented with a glass balance spring. This was much less affected by heat than steel and didn't rust. The balance spring and the balance wheel form a harmonic oscillator. The balance spring provides a restoring torque that limits and reverses the motion of the balance so it oscillates back and forth. Its resonant period makes it resistant to changes from perturbing forces, which is what makes it a good timekeeping device. To derive the motional equations, we use Newton's second law. The restoring torque can be written as negative kappa theta, also equals I alpha, where I is the moment of inertia and kappa is the spring coefficient. The following differential results from simplifying the above equations. And the solution of this equation is simply a sinusoidal wave, just like this. The period of oscillation can be extracted from the above results. T equals 2 pi multiply the square root of I over kappa, and the angular frequency is omega equals the square root of kappa over I. And thank you.
Hello everyone, my name is Lin Zerui. My student ID is 109610017. Also Jason Lee. Let's talk about the materials. First, we have to use different kinds of ropes and weights. Something can handle ropes and protractor. The picture is schematic diagram. According to the period of pendulum, T equals 2 pi root G over L. We have known that the gravity G and the length of the rope I, L are variables. But we have to realize that if the angle is small enough so that T can hold. Let's talk about our plan. Our plan including two parts. One, pendulum, and spring. The parameter of pendulum is angle, length, mass, materials difference. Let's talk about the steps of pendulum. Step 1, test how small the angle is. In our plan, we choose 20 degrees perpendicular to ground to be the initial angle. reduce the angle by 5 degrees per time. Then we can measure the angle which satisfies the formula. Step 2. Find the gravity of the experiment place. As we learned from the physics course, different altitude will make a difference in gravitational acceleration. So first, we need to find the altitude of the place where we do experiment. Then we can know the gravity G there. Step 3. Change the length of rope and measure period T. This step is to find the deviation between the ideal value and experimental value. We will choose 3 different lengths of rope and then measure the period. Before doing the experiment, we estimate that period will be larger than ideal value because of friction and air resistance. Step 4. Change the mass of weight and measure period T. This step is to find the deviation between ideal value and experimental value. We will choose 3 different mass of weight and then measure the period. Before doing the experiment, we estimate that the period will not change. Step 5. Use different ropes to verify if it affects the consequence. In this step, we will compare different types of rope with same weight and observe what the result is. Include nylon rope, cotton rope, and so on. Well, as for spring, change the mass of weight and measure period E. Maybe we will try to DIY a pendulum clock. Thank you.
Maybe we will DIY this pendulum clock like this.
这个解密钟很容易做，我希望你也能马上行动。